Thanks. Thanks, York, for the introduction. The title of my talk is Why Scaling Matters in Hydrodynamic Turbulence. So what I'm going to do is I'm going to give you a survey of the typical topics that one concerns themselves with when talking about scaling exponents. And I'm also going to motivate why scaling exponents are useful. I'm going to give you a particular case where going after the scaling exponents gives you a different result. So just a bit of introduction. Scaling in turbulence is a very old topic. So the first interest in scaling was about the second order velocity difference. Here I'm showing you the second order velocity difference between 2 points in space. This is the velocity difference between 2 points, and this is a vector. And you can take its magnitude and calculate its moment. And the prediction was that this second order moment, normalized appropriately, will scale as r power 2/3, where r is the separation magnitude between these 2 points. And this scaling occurs in a range which is known as the inertial range. It's bounded below by the Kolmogorov scale, which is a measure of the smallest eddies. And on the top, it's bounded by an integral length scale, which is the characteristic length scale of the system. And this scaling is supposed to hold as the Reynolds number of the system increases asymptotically high. So as Re here increases towards infinity, the scaling becomes manifestly more vivid. Nu here is a fluid kinematic viscosity, and this was first noted by Batchelor. This is 1946. He gave a summary of this result by 3 independent works. One was by Kolmogorov, and the other was by Onsager, and the third one was by Heisenberg and Weizsäcker. Note in this paper, Batchelor in fact talks about the parallel velocity differences. These parallel velocity differences are also called longitudinal velocity differences. And all you do is you take these velocity increments and you project them along the separation vector. And these are the separation velocity increments that one typically calculates in experiments. So I will also provide some context with that. So the basic idea now is I would like to show you how these exponents are calculated for a given order, and then I will proceed with other orders without explaining how these exponents are calculated. Here I'm taking the lowest non-trivial order. This is order 2. And you see that I'm showing you this second order absolute velocity structure function, which is shown here. And I'm plotting this as a function of r, which is normalized by the system size. And this data is coming from direct numerical simulations of homogeneous isotropic turbulence. This data is, the boundary conditions are periodic boundary conditions. This is a wall-less flow. There are no walls. And you assume constant density, so this is an incompressible flow. And these simulations are forced, so you have an energy input. And what you basically are doing is you're shaking the box vigorously, and you're adding in energy, and the energy is being added at the low wave numbers. Here I'm showing you the 3-dimensional energy spectrum as a function of the wave vector. In the computations, this energy is in fact being added spectrally, and you're adding them to the low wave numbers or the large scales. And as you keep decreasing the viscosity, this is how we change the Reynolds number in simulations. You'll have this scaling range that develops. And with increasing Reynolds number, you see that this scaling range becomes broader and broader, as I just told you. And this intermediate scaling range is approximately -5/3. And what you're seeing here is the physical space counterpart of this. If you take the Fourier transform of the 3D energy spectrum, you will get this quantity. And you see that you have a similar trend there. As you go down in scale from the large scales to the small scales, you see this vividly manifest scaling range. At the smaller scales, you'll see a quadratic behavior for the second order structure function. But as you go to larger scales, you see that the slope decreases. And the slope here, I'm representing it by r power zeta 2. Zeta 2 is the second order scaling exponent. And note that zeta 2 is less than 2, as you can clearly see. So the flow is non-smooth. So the thinking is as you increase the Reynolds number or you decrease the viscosity, this non-smooth inertial region, this will grow with Reynolds. And the question that I would like to ask is, can we say something about this scaling exponent zeta 2, which is irrelevant of the flow details? So notice here that I have marked the region in the large scales where the energy is input. This is corresponding to this. So in different simulations, you might have different mechanisms of energy input. In these particular simulations, we are using a frozen energy injection. in experiments, you will energize the flow differently. So can we say something about these exponents? And these exponents are useful because they quantify the statistical signatures of the flow. For instance, you see these great variabilities in velocity increment structure functions. These exponents, in fact, give you a mapping on the real line for this intermittent behavior of turbulence. So these exponents are very handy. They give you a quantitative feel of how turbulent the flow is. So what we do is we plot these second order structure functions versus the scale separation on log-log scales, and you would like to measure this inertial range. Here I've marked this with a dashed line, and I've also indicated the energy input. And what we typically do is we calculate the logarithmic local slope. So we take this quantity on the ordinate, we do a logarithmic derivative like this, and we get these curves. And if you have a power law, then this local slope should give you a constant plateau-like behavior, which is what you see here. And here I'm showing you from left to right, your Reynolds number is increasing. And you see that as your Reynolds number increases, you see this broad range develop. And this is zeta 2. So you'll fit a horizontal line there, and you will call that the exponent. This is how you calculate it. In this panel here, I'm showing you a blow-up of this local slopes. Notice that when you look at this local slopes in even more magnified manner, you'll see some variations. And these variations will constitute these error bars in these plots. And note that the local slopes is a very useful method of calculating exponents because you have a linear ordinate. Here you have a heavy compression. So you could also do a least square fit, but in a local slope method, you are calculating things with much more accuracy. So the plot you see here is the plot of zeta 2. This is the absolute second order structure function exponent, and I'm showing it as a function of the Taylor scale Reynolds number. The Taylor scale Reynolds number, think of it as the square root of the Reynolds number I just introduced. And this is done because in the literature, typically this R lambda is the Reynolds number that's shown. And what you see is these exponents seem to increase with Reynolds number initially, and they seem to saturate. I've also shown you the Kolmogorov non-intermittent value of 2/3 here. This is based on the self-similar prediction that I just showed you, that zeta 2 is 2/3. And you see that there's a clear deviation, especially at higher Reynolds numbers. And it seems to saturate at around 0.72. So this is an anomaly. And this is can be quantified not only as order 2, but different orders. And this gives you a measure of how intermittent the flow is. So at higher orders, greater the deviation from the self-similar scaling, you can expect higher jumps in your velocity field. So also note that this computed flow is smoother than the K41 prediction. What I really mean by that is these exponents are closer to the value of 2, which is the smooth condition, rather than the Kolmogorov prediction. So now I'm going to show you the same plot that Srini showed you in the morning. So this is the second order scaling. What we have done is we have compiled all the second order exponents from the literature, and I'm plotting now the longitudinal exponent. So this is the parallel velocity projection as a function of the separation distance, and I'm plotting it as a function of the Taylor scale Reynolds number, which is the square root of the integral scale Reynolds number. And what you see is most of the data here lies above the solid line. The solid line is the Kolmogorov self-similar scaling, and the dashed line here is the model prediction by Sreenivasan and Yacob. You see that the data, the preponderance of the data seems to follow this model prediction rather well, more than the Kolmogorov scaling. And I've also shown experiments and DNS data here. And I have a chart here which shows you more information about the data, but the details are not important. What one must appreciate is all these empirical data all have their own peculiarities. So in fact, in experiments, you do a 1D cut, whereas in DNS, you can have a 3D measurement. So you can have components in all the 3 directions, for instance, or you can calculate the isotropic projections. And typically one calculates these experiments also using a method called ESS. I'm not going to go into the details, but you compare the slopes at order 2 with a different order, and you compute these exponents somehow. So all these empirical data, starting with that of Van Atta in 1972, which is shown here, all have different methods of calculating, and they also have their own peculiarities. But you see that the consensus is that the majority of the data is lying above the self-similar prediction. you also see that this DNS data is smoother than the experimental data. And you see the DNS data here, the symbol here is Goto's data. You see that it's closer to 2 than the experimental data, which is the solid symbols. So one can do this by varying this order 2 and going to yet higher orders. So what you can do is you can vary this P to 3, 4, 5, so on and so forth. Note that the Kolmogorov prediction is P-thirds. This is the linear scaling. This is the dimensional value. And I'm going to show you the same thing now for the 4th order. I'm not going to repeat how I calculated the exponents. I already showed you that at order 2. But again, I plot everything that I could get hold of. So I'm showing the 4th order exponent. Again, this is the parallel component or the longitudinal exponent as a function of the Taylor scale Reynolds number. And you see that the consensus is that the majority now lies below this self-similar prediction of 4/3. Again, this DNS data is smoother than the experimental data. So notice that this DNS data here and lies above this experimental data. Although there are some experiments like from the group of Antonio et al., which are very close to the 4/3 line. So the majority of the data seems to disagree with the Kolmogorov scaling. So the basic idea in these 2 slides I wanted to give is there is correction to these scaling exponents. And this correction, in fact, is useful and it's important because this scales are very small. So even if you have a small difference in the exponent, it can produce a large jump in the velocity difference field. So here I'm summarizing both these plots that I just showed you. Notice that for order 2, that the zeta 2 is greater than the Kolmogorov scaling, whereas it's reversed for order 4. It's the measured exponents are less than the Kolmogorov values. So I skipped order 3. So I'm going to ask the question, what is zeta 3 and how does it evolve with Reynolds numbers? So zeta 3 is, again, I'm going to take the velocity difference magnitudes. This has a combination with longitudinal and transverse data. So you will see that the exponent, I'm going to call it zeta 3. And before I get to that, I would also like to address why zeta 3 is useful anyway. Why do we care? And this part of my work is a joint work with Theodrivas, Katepalli, Sreenivasan, and Gregory Iyer. So before I talk about zeta 3, I would first talk about dissipation scaling. This was introduced by Srini in the morning, so I'm going to be quick here. Again, the mean dissipation is given here. Notice that for laminar flows, I'm going to introduce the terminology D, which is the normalized dissipation. We're normalizing the dissipation with a velocity scale and a length scale. These are large velocity and length scales. And for laminar flows, the exponent is -1. However, for turbulent flows, the general consensus is that this D, this normalized dissipation, as you increase the Reynolds number or you decrease the viscosity, this goes to a value D star, which is positive. And you see here this DNS data compiled by Sreenivasan in 98, and this has R lambda till 200, and this shows that it drops from the laminar regime and it asymptotes to a constant in the higher Reynolds number regime. And note that for an inviscid Euler flow, the mean dissipation is 0. This turbulent dissipation is also called anomalous dissipation because as the viscosity is going to 0, the symmetry breaking parameter is vanishing. The dissipation is not non-vanishing. This is also called anomalous dissipation. Notice that from the basic consensus, the D star is of order 1, and this has some non-universalities to it, and this is well known. And this is also known as zeroth law of turbulence because this is the basic founding tenet of, say, the Kolmogorov theory. The question I would like to ask is, as you send viscosity to 0, what happens to D? So this normalized dissipation goes as RE power minus alpha. What is alpha? If it's 0, then you have the zeroth law. If it's a number between 0 and 1, 1 is the laminar case, then the anomaly should vanish. So in order to address this, I will use scaling data. And this work is motivated by Onsager's theorem. Onsager is one of the first people to realize there's a connection between large scale quantities like mean dissipation and the small scales. And what he said was, it's possible to show that the velocity field in such ideal turbulence is this in the asymptotic limit, cannot obey any Lipschitz condition of the form where this velocity difference between 2 points in the flow is less than r power n, this is like a Holder condition for any order n greater than 1/3. Otherwise, energy is conserved, which means that the mean dissipation should go to 0. What this means, the upshot is that this normalized dissipation goes to 0 as viscosity goes to 0 or Reynolds number goes to infinity, unless this local Holder exponent is less than or equal to 1/3 at some place in the flow. In other words, if the local Holder exponent is greater than 1/3 everywhere, then the mean dissipation must vanish. So the goal here is to attack this problem using the scaling exponents now, because so far everyone has been looking at just the mean dissipation and you study its trends with Reynolds numbers. So we are doing something different. And Onsager's theorem was proved by Constantine, E, and Titi. And what they did is they considered velocity difference magnitudes here. They considered the third order moment, and they assumed these power law bounds with these scaling exponents zeta 3. And if these bounds are satisfied for all scales less than the characteristic length scale of the system, then they showed rigorously that this normalized dissipation will go to 0 as viscosity goes to 0 if this exponent zeta 3 is greater than 1. Conversely, if this anomaly must survive, then this third order exponent must be less than or equal to 1. Notice that unity is the Kolmogorov value, and the Kolmogorov scaling is consistent with the 0th law, or the strong dissipative anomaly. Furthermore, this was also shown by Duchamp and Robert and Drieves and Eink. Drieves and Eink went a step further. What they did is they obtained a direct estimate using the Navier-Stokes equations, and they showed an upper bound for this normalized dissipation. They showed that this dissipation has to be bounded by Reynolds number power this, and this gives you the minimum dissipation decay exponent. So if zeta 3 is 1 or smaller, then the d has to go to a constant asymptotically. But if it's greater than 1, then d must vanish in the limit at a minimum rate which is given by this. One can also use the Kolmogorov 4/5 law and show that if this longitudinal exponent, these are what are calculated in experiments. So if these are greater than 1, then the normalized dissipation must vanish in the limit, and this I showed recently. So the Kolmogorov 4/5 law is not in violation to the vanishing anomaly case. So that's an important point to make. So this Onsager's theorem has a few assumptions. All the papers I cited make these assumptions, so I wanted to go through these assumptions and see how the DNS data stand in scrutiny of these assumptions. The first assumption is that the third moments are bounded. These are the absolute moments. So this U is the characteristic velocity scale, and these third moments have to be bounded. So an obvious choice would be to take the characteristic velocity scale as this. This is the cube root of mod U cube. This should be mod. However, this is not the traditional choice. People typically take the RMS velocity fluctuation as the velocity scale. So in order to see if this traditional choice stands up to scrutiny for the DNS data at hand, I have plotted here as a function of Reynolds numbers. I have plotted here this ratio between this mod U cube and this mod U square raised to the power 3/2. And I'm showing this here, these red symbols here. And on top of this is the analogous quantity for a Gaussian random field. This is a synthetic field. Notice that the DNS data across Reynolds numbers are bounded by that. And if you take the components instead of taking the full velocity vector, you will also see that the corresponding component ratios are also bounded by the corresponding Gaussian value. And this is shown here. And this is well known. The large scale fluctuations are sub-Gaussian. They are slightly sub-Gaussian. And you see that you can now take this characteristic velocity as the RMS velocity fluctuation. So this is one of the assumptions of this theory. And the next assumption is this power law bound. They assume a power law bound of this sort. And here's where the scaling theory of turbulence kicks in. Because these structure functions show these beautiful power laws, it's very easy to check whether these power law bounds are satisfied. For instance, here I'm showing you the third order absolute velocity structure function, which is normalized here as a function of the scale size. L here is half the box size. This is the periodic box that I showed. I'm choosing L as half the box size, and I'm plotting this here. And what you see is you can use a matching condition to determine this proportionality factor in the power law. And you can get the C here. And this C subscript T, it the subscript t is there because it can be time dependent in the theory. This has to be something larger than this constant. And there are more sensitive checks to see whether this Ct is dependent on viscosity or not. And to the best of my abilities, what I see is this constant C is independent of the Reynolds number of the viscosity. So this is the second assumption. And the other assumption now is to get this value zeta 3. And the zeta 3 is obtained something like this. So because this scaling behavior is shown by this total structure functions, this absolute third order structure functions, we can plot these exponents. These exponents are obtained similarly to what I showed you for order 2. You can use local slopes and you can plot this zeta 3 and having a subscript nu to show that there is a Reynolds number dependence. I'm plotting it as a function of the integral scale Reynolds number, and these diamonds are the data. And what you see is they, at low Reynolds numbers, they are below 1. 1 is the Kolmogorov value, but as you go to higher Reynolds numbers, they are increasing. And they seem to be saturating for this DNS at some value that is greater than 1. So what you do is you pick zeta 3 as max of zeta 3 nu, and you do that because you're looking for an upper bound. Notice that R over L is a number that's less than 1, so you want to pick the worst case to form your upper bound. So you'll pick zeta 3 as the maximum of zeta 3 nu. In order to do that, what I have done is I have done some least square fitting. I have assumed this form for the third order exponents. This is zeta 3 plus alpha Reynolds number power minus beta, and I've fit the parameters. I've taken more complex functions as well with logarithmic corrections, and you can get values for this zeta 3 alpha and beta, and this fitting procedure gives the value of zeta 3 to be 1.071, which is greater than 1. So as per the theory that I just showed you, if the zeta 3 is greater than 1, and if this is zeta 3 is the asymptotic value I have obtained from the fit, then the dissipation has to vanish in the limit. Now, there are very few works which have reported this value of zeta 3 nu. So I'm going to next compare how this fit value and these exponents fare with the zeta 3 nu from experiments and simulations from other groups. And this is what I'm doing here. I'm showing you here the third order absolute exponents and the third order parallel or the longitudinal exponents. I'm showing it to you as a function of R lambda. This is again the square root of the Reynolds number. You typically use this when you're comparing across different works because this is prominently given. And notice that again, you see the same trend. At the low Reynolds numbers, you see that the exponents are less than 1. And as you increase your R lambda, these exponents go greater than 1. And I'll point you to the highest Reynolds number that have been calculated. This is by Sreenivasan and Dhruva. This is at a Reynolds number of 10,000. And notice that here, the error bars are large. So there is considerable scatter in the data. And notice that this is the helium experiments by Bellin et al. Even the exponent is greater than 1, but again, there's considerable scatter. And the solid line here is the least square fit I did to obtain the zeta 3 from the zeta 3 nu. And this is how it compares with the data. So the overall trend seems to be that zeta 3 nu is greater than 1, especially at higher Reynolds numbers. Also notice that there are some outliers here. This is the data from Van de Water's group. These are experiments in jet turbulence. So even the experiments show that the exponents are greater than 1. But I would like to point out that in Dhruva's thesis, the data is 1.03 plus or minus 0.03. So there is a possibility of it also reaching 1. We should not exclude that possibility. But the overall conclusion, my conclusion is that the exponents are greater than 1 so far. What happens at higher R Reynolds numbers, I do not know, because there is no restriction on these exponents. They can fall down as well. Now that we have zeta 3, so zeta 3 is the zeta 3 I got from the fit, and it agrees well with the literature. So I'm going to use this to check if the dissipation data obeys the Drivas-Iyer bound. I remember that the bound is the minimum decay exponent. So I'm going to do this. So I'm showing you here dissipation scaling. Again, this is the normalized dissipation. This is the Drivas-Iyer bound. This is the minimum decay exponent. So what I'm going to do is I'm going to multiply D, which is the normalized dissipation, with Reynolds number power this minimum decay bound. So this is a compensated plot. And I'm showing it to you as a function of the Reynolds number, the log scale on the horizontal axis. And you see that except for the smallest Reynolds number, this corresponds to an R lambda of like 64. All the data fall on this horizontal line. So this compensation with the exponent data works for the dissipation data. So you can show this in a few other ways. You can also calculate the logarithmic local slopes for the dissipation as a function of Reynolds number and show them on linear ordinate. You see here that this is what I've done, and 0 here corresponds to the case where the anomaly holds. And you see that this data, except for the two smallest Reynolds number data, fall on this red line, which is close to minus 0.05. And if you do a least squares fit, again, I'm only fitting for all data excluding the last two, because the local slopes tells me that the scaling is really at the higher Reynolds numbers. You will see a value that is consistent with the value that you obtain from the exponents. So what you see here is the dissipation, the large scale data is giving you a decay rate, which is consistent with what the small scale statistics are telling you. So the normalized mean dissipation agrees well with the zeta 3 that is obtained from the third order scaling, and this indicates a weak anomaly. So this normalized dissipation goes as r e power minus alpha. If alpha lies between 0 and 1, this is a weak anomaly. If alpha is 0, this will be a strong anomaly. Note that in laminar case, this will be 1. So because this exponent here is minus 0.05, this is a weak anomaly. And note that if you have a weak anomaly, most of the things that we know about turbulence still holds. For instance, the mean entropy will still diverge because this mean dissipation is vanishing very weakly. So this is almost nu power minus 1. The rate is not as strong, but it still goes to infinity as Reynolds number goes to infinity. But one can also fit the dissipation data using what people have been fitting so far. So you can also do a power law plus a constant decay, plus a power law plus a non-constant value, and this is what I've done here. So this is the same dissipation data I showed you. The dissipation data is fitted with this curve. This is a power law plus a non-zero constant, so I've assumed d star is greater than 0. And notice that even this fits the data well. It doesn't fit the data as well as the power law, but the goodness of the fit is more or less the same. And the d star value is of order 1. This is the case for the strong anomaly. So this here, d goes to d star. So alpha here is 0. You're assuming that alpha here is 0. And d star is greater than 0. But this, the problem I have with this is it contradicts the third order trend. So one cannot have the same simulation telling you two different pieces of information from two different scale ranges. So the only problem with this is this contradicts the zeta 3 new trend. And this is the traditional scaling, and this supports the argument that there is a strong anomaly. In the morning, there was also some talk about the relation with the dissipative anomaly in the 4/5 law. So I put down the Kolmogorov 4/5 law here. This is what the 4/5 law is. And notice that if the mean dissipation goes to 0 in the limit, what it's telling you is that the third order longitudinal structure function, this is the sign quantity. You're no longer considering the absolute value. This, in relation to R, is going to 0. So what you're saying is this S3 is going to 0 faster than R as R goes to 0, and the field is becoming symmetric at order 3. This is what the vanishing anomaly case tells you. So the vanishing anomaly case is not inconsistent with the Kolmogorov 4/5 law. This is the empirical data from our DNS. What I'm doing is I'm plotting the right-hand side. This is minus S3 divided by R. On the horizontal axis, I'm plotting R over L0. L0 here is half the box size. I'm showing you this data for 3 Reynolds numbers, and I'm also plotting the mean dissipation for each of these simulations. Note that as the Reynolds number increases, this S3 divided by R is decreasing, and it's forming a nice plateau here, you can see, and the corresponding mean dissipation is also decreasing. So this supports the argument that the 4/5 law is consistent with the vanishing anomaly case as well. And one must know that the validity of the 4/5 law cannot be taken as evidence for 0th law. And in fact, Bedrosian et al. Have shown that the 4/5 law is consistent with a weak anomaly. Again, a weak anomaly is when it disappears at a rate where the exponent is lying between 0 and 1. So this is an important point to be made. So there is no inconsistency. There are no exact laws being broken if the vanishing anomaly case occurs. So I would like to conclude my talk by observing the following. What we have done, we must qualify our statements. So what we have done is we have shown that for a DNS on the periodic cube of length 2 pi with frozen large-scale forcing, the normalized dissipation weakly vanishes as RE power minus 0.05. D here is the normalized dissipation, and note that as RE tends to infinity, this will go to 0. And however, there's evidence for strong anomaly in other setups. For instance, if you take wake behind grids or pipe flows with wall roughness, there is very good evidence that the strong anomaly survives. And here I'm showing you data by Sreenivasan. This paper shows you data for wake behind grids, and you see that the data shows very strong support for the fact that the anomaly survives strongly. What all this tells me is that this is homogeneous isotropic turbulence on periodic boxes with this body force. It has seemed to show evidence for strong anomaly without fluid interactions with solid walls, and that was the allure of DNS on periodic boxes. There are no walls, but it is still showing you that the gradients are amplifying at a rate that the mean dissipation is remaining constant. This may no longer be generally true. It might depend if you take a different forcing. If you might take a larger box size, you might see a different result, but it doesn't apply universally for HIT flows with periodic boundary conditions that these things happen. And Bedrosian et al. Have also considered a different large-scale setup, but with periodic boundary conditions, they have shown a weak anomaly. So our data is consistent with Bedrosian et al.'s work, but with a frozen energy forcing. So this is the main crux of my talk, that this getting scaling and going after these problems using the scaling exponents is much more fruitful than calculating the mean dissipation and working on the Reynolds number trends. The reason being that the mean dissipation is a large-scale quantity. It takes a lot of time to evolve. So at higher Reynolds numbers, experiments and simulations need to run for a very long time in statistically steady state. Exponents, small-scale quantities, have shorter time scales. So you don't have to run such long records. So it's easier to solve or address this problem in a meaningful way if we were to hang behind the scaling exponents and not necessarily the mean dissipation, the integral scales, and the URMS. So this is what I wanted to say, and I would be glad to take any questions. Thanks a lot. I don't know. I'm not claiming that the anomaly will survive or not in a different forcing scheme. I'm giving you one class of flows, DNS, where the anomaly is weakly violated. One needs to do this one needs to do this as a community.
So there is one major difference between what I have here and what you tried to show without some details. And that is, there was no problem measuring the dissipation here. The turbulence was decaying according to a power law. So you fitted it with a power law and you got the dissipation. You didn't have to measure it. In other words, the resolution with which you measure did not matter, because all that I had to do was to measure the energy accurately, not the energy dissipation. Okay. When Kaneda did his 4096 cube calculations, if you remember, his last point was a little bit below the rest of it. So at that time, I actually computed using a form for the energy dissipation or the spectrum at very large wave numbers, how much correction would it produce? And it actually bumped it up to bringing it to the flat level, as I have tried to tell you many times. And therefore, a similar thing has to be done for the simulations data you have presented, because the resolution here is not very good. You know that very well. And so that is one major point. And the other thing is, it's not true that in pipe flows and with wall, etc., the dissipative anomaly is valid. I know Greg keeps saying that, and you keep saying that, and it's not true at all. In any case, the other point to mention what Grisha was talking about, if you go to the graph with zeta 3, all the data plotted, this one here, I've been telling Kartik many times that for the 10 to the power 4, he has 2 points. One is 1/10 of the data that was used, and the other is the full data set. The full data set is the one that gives you 1.03. And a fraction of the data, I don't exactly remember, it's 1/10, gives you the higher value. So if in fact you take the whole data and not only a fraction of the data, the tendency of this curve is for it to go up and then to come down. I mean, I'm not claiming that it is so, that it is entirely possible. So eventually this actually goes back to unity and you have the whole thing recovered. And in fact, if the best fit you have really misses a whole lot of data points here. And if you take them and fit them better, as I have done, the tendency is for the whole thing to go up for whatever reason and come down for whatever reason. And I don't know if it is true or not, but what I'm saying is you should be careful. You have to put all these caveats in front before we actually conclude anything. It's a very important point, and I really think it is worth it. This whole thing has been really driving me up the wall because I can't get these very basic elements through to my co-authors. So I think there's a whole lot of things behind this than just saying, well, there is a weak anomaly. In one case, maybe there is, maybe there isn't, as you showed, it just fits nearly as well by something that asymptotes stay constant. So what we should say is we should be careful about how much you can commit yourself to at this point based merely on the data. I think that's where I would stand on it.
Thanks.
Can I? Okay. Thank you, Kartik, for the very nice talk and very accurate data analysis that, if true, opens a very important theoretical question, as you say. Let me take the same point of view of Srini. Let's suppose we want to be very cautious and trying to explain everything, for instance, by the reason that we are underestimating the error bars. You didn't mention two points. First one, that in the experiments you have anisotropic corrections, and therefore it's always, one has to always take it a little bit with congrano salis, the experimental results, unless they are able to disentangle the small anisotropic corrections. And the second point is the Reynolds dependency. I mean, I think it's very, it might be very risky to pretend to know what is the functional dependency on Reynolds, as you did. That is what also Srini is saying, right? Unless you have a very good reason to predict that dependency, you are putting a strong bias on this point. That's, I hope you agree. What I would urge you is to calculate the longitudinal and transverse for the second order, the longitudinal for the third order, and the mix, the two transverse and one longitudinal, because we know that if homogeneous anisotropy statistics holds, they must scale in the same way.
Not for order 3.
No, the longitudinal and the transverse second order, they must scale the same. Do you agree?
Yeah, I agree.
And the two third order, the fully longitudinal and the double transverse plus the longitudinal, because of incompressibility, they must scale the same.
Yeah.
So any discrepancy would give you a systematic error due either by Reynolds or by Reynolds anisotropy in the experimental case. So this, I think, it's the step that is missing in this analysis. What do you think?
Thanks, Luca, for the comments. I forgot to mention this theory doesn't require any isotropy or homogeneity assumptions. The theory of Greg Eink and Theo Drivers and Constantine et al., there is no assumptions of isotropy. The only real assumption is the power law bound. And but the second order relation that you're talking about, we have in fact seen it, myself and Srini, we have published it in 2020 we've already done that. So the exact relations at order 2 are satisfied for this DNS data. Yes, within error bars, yes. I don't recall the details right now. I'll be happy to send you the paper. But we have checked that. For order 2, there's an exact relation in order 4 as well. We have checked that. For the third order, the only relation I know is the 4/5 law. But that assumes mean dissipation to be non-zero. There's an implicit assumption there. It assumes that the mean dissipation is non-zero at order 3.
So to sort of make a related point that to Lucas, Kartik was careful to say that this is true only for this particular flow. He is not implying, or he should not be implying, that it is valid for grid turbulence or homogeneous isotropic turbulence, etc. Because it turns out this particular flow is not really satisfying some conditions of isotropy that of the sort that Luca is talking about. In particular, because the box size is small and the forcing scales are large enough that, in fact, the correlation does not decay to zero from one end of the wall to the other end of the wall. So that means it is not strictly isotropic homogeneous turbulence, but it is a flow with a periodic box, and it satisfies what it does. And so for that particular flow, this may well be all true, but you cannot even extrapolate to say for homogeneous isotropic turbulence, it is true. It just can't be done. So he said this, but it was not entirely clear. Would you not agree with what he said?
I absolutely agree. Yeah, that's what I said in the...
Yeah. So it is some flow. I mean, some flow that is close enough, but not really the full thing.
But note that you don't require any isotropy or homogeneity for this theorem to hold. So we are testing an exact mathematical result. We're calculating the exponent. It doesn't require any stipulation of homogeneity or isotropy. If it's greater than 1, it has to decay.
Is it the case?
Yeah,
Sure.
They have no assumptions. So far...
It has to be so, at least on scales, where Fortnig's law is valid.
No, the result that I showed for the longitudinal, that's on the range where the 4/5 law holds. Their theorem doesn't even require that.
So all one can say is at this point, you have...
Yeah. So the zeroth law is not a done deal. So I think we must address these questions so for it to be a law, in my opinion. For HIT, I'm not talking about grid turbulence and things like that. I'm talking about these periodic box flows.
Since we are doing the laundry in public here, I might as well add another point. Yes, and that is when Kartik normalizes his dissipation data. Traditionally, it is the integral scale of the flow and the velocity, which is the square root of the energy or something like that. Now, he is using for the length scale the size of the box itself. And technically, in DNS, the size of the box is supposed to be much larger than the integral scale of turbulence. But here, because the correlation doesn't exactly decay all the way, you can't even say that. So he's using the size of the box, which to me is a big headache. Well, we have to resolve it somehow or the other. And that's something also for you to keep in mind. So if he chooses an integral scale, which may bear a ratio to the box size, which is different at different Reynolds numbers, it is conceivable that he will actually get a slightly different relation. So there are all these many things about the data one has to be mindful about and one has to spell out before the audience or the readers can assess whether it means anything or not. You see, for example, here, the curve number,
so
the top curve.
This is what Srini is talking about. I'm plotting the longitudinal and the transverse autocorrelation functions for two boxes. One is of length 2 pi and the other of 4 pi. The 4 pi, the correlations decay as you go to the box edge, but for the 2 pi box, the correlations don't decay adequately as compared to the 4 pi. And I'm also showing f plus 2g divided by 3. This is how you calculate the integral scale in a periodic DNS. You don't calculate integral f of r, you calculate this integral. And these decay for both the different box sizes. But regardless of this, the exponents seem immune to this. Look at this, 2 pi cube and 4 pi cube at a fixed Reynolds number of 400. And the local slope here, -1. So this at r lambda, it's 1. So this is give you 0. This is giving you 0 here. The point is the way we are trying to address this is by calculating the exponents, and I don't think these non-decaying of this correlation functions are affecting the third order exponent. That is the...
Yeah, we don't know that, in my opinion. Also, for the 4 pi case, it's decreasing for the longitudinal. For the transverse, it has to go up and go down and go up again, as it does. But the integral has to be, integral of the negative part has to be half of what it is for the positive part, which is very far from being true here, you see. I mean, you know what I'm saying? So there are issues related to all this. So all of this says that for this box, for these calculations, this is what you find. But when you generalize it to something else, you have to put in 100 caveats, at least 100 that I can think of.
I agree. One must not generalize these results to anything other than what I've shown.
I think that's a nice closing comment, and I would thank Kartik once more for his presentation. And